All right. So this is the problem we're going to start with. We're told to calculate the pH when, in part A, 49.0 milliliters of 0.100 molar NaOH. And this particular situation is a strong acid, strong base titration. What do we know about strong acid, strong base titrations? They are a situation that results in actual neutralization. Remember we talked about that last week. Okay? Yep, we're doing number 1 under the acid and base. Yep. Added to 50 milliliters of 0.100 molar HCl. So that's the situation in part A. The second situation is 51 milliliters of the base added to, again, 50 milliliters of the acid. Okay? All right, so the first thing we obviously want to start with is going to be our overall equation. We know we're adding hydrochloric acid to NaOH. We know one of the products is going to be H2O because the proton will donate itself to the hydroxide group in an acid-base reaction. We also know that it will form NaCl, which is aqueous. In other words, does this matter? No, it does not. We don't want to know anything about this. We want to know about pH, which involves something over here with H+, right? The other thing we want to know, do the chlorine or the sodium matter on the left side? No. If we don't care about it over here, we don't care about it over here. So this becomes the neutralization reaction. And this is only for strong acids and bases. All right, from there, using an ice table, ladies and gentlemen. When we put stuff into our ice table, what are we usually putting in there? Molarity is correct. Do we have to take into account this 50 or 49 milliliter, 50 milliliter situation? We absolutely do. Before we add these two things together, they're by themselves, the 49 milliliters and the 50 milliliters, right? When we add them together, their volumes combined to become 99 milliliters. So what we need to know is what the concentration is going to be of these things once they've combined together, right? Sound correct? That's the stuff we want to put in initially. We want to know concentration after addition for all titrations moving forward. So we have to do a little calculation before we can do the ice table calculation. So we start with 49 milliliters. How many liters is that? Thank you. Of the 0.1 molar, of NaOH, which looks like this. When we calculate how many moles we're going to get, 4.90 times 10 to the negative third moles of OH minus. Now, something we've talked about with ice tables is we have to put in molarities. But since we know the final volume is going to be the same, could we theoretically just use moles and calculate a volume at the end? Absolutely. So let's just use moles in our ice table. That way we don't have to do a further calculation. We'll do that further calculation at the end, and you'll see why this saves you some time. We got to do the same thing for HCl. We've got 50 milliliters of 0.1 molar HCl. How many liters is 50 milliliters? 0.050 liters times 0.100 moles of HCl over 1 liter. Wow. That's going to get us moles of HCl. In other words, moles of H plus, remember. Because we're assuming that HCl is H plus, and we're assuming NaOH is OH minus. All right, and like I said, for these types of problems, we can use moles in the ICE table. All right, so now we have initial information, right? We're told we start with this 50 milliliters of 0.1 molar HCl in the beaker. So I'm going to put that concentration here. From there, we're told we're adding the 49 milliliters of NaOH. So there isn't any to start. But we do add some. Now, what do we know about H and OH? What are they going to do? They're going to completely react to form everything they possibly can on the right side. Do we care how much water they form? No, we don't. But we do need to recognize that this number is a negative number. And this is our change on both sides. Why? Because this is going to completely consume as much of this as it can. It may actually consume more. And we may have left over this. But we have to see that when we add something that opposes the original concentration, it's the change. So when we add something that opposes our acid, like a base, when in a strong acid-base titration, this is the change that is going to occur as a result. That's going to leave behind this. That's going to leave this. Technically, we don't fill this in. A lot of times we've assumed it's 0, but that kind of screws with your head if you do that here. Okay? This is what we added. All of it completely reacts. That's the definition of a strong acid, strong base reaction. It all completely reacts. There's a little bit of H plus left over, right? Yep. What's up? Yeah. So I'm going to move this. So I just put the 0.1 because you can see that 5.0 minus 4.9 is 0.1. Does that make sense? But this is really 1 times 10 to the negative 4th, right? And remember, we're using moles. Our goal was what? Our goal is pH. What do we need for a pH? We need a concentration of H+, right? Concentrations are in moles per liter. So now we have a concentration, but now I have a number of moles, but I need a concentration, right? So at equilibrium, what's the total volume of the solution? Where'd I get that number from? 49 plus 50 makes 99 milliliters. Divide by 1,000 gets you 0.099. My concentration comes out to be approximately this. Taking the negative log of this number, gives me a pH of about 3. Strong acid-base titrations, as we saw using those curves on Friday, are going to start at very small numbers and jump very quickly up to big numbers when we pass that equivalence point. Yes, ma'am?
Where did you get the 0.099?
That was the total volume. That's the 49 plus the 50.
Oh,
that was my total volume after we added both together. Does that make sense? Okay. What else did we talk about on Friday as far as what we know at the equivalence point? What does it mean to be at equivalence? May you remember? Not necessarily, no. Say again?
Amount of acid equals that of things.
The concentration, not concentration, sorry. The moles of your hydrogen ion should equal the moles of your hydroxide ion at equivalence only. Okay? For this particular exercise, can you see where the equivalence point should be? Since they're both the same concentration, if we had the exact same volume, like 50 milliliters, we could calculate what the pH is at equivalence. But what'll happen is this would become 0, this would be 0, our pH would be true neutral, so 7. Because it's a strong acid, strong base, remember that's where equivalence points are for those types of reactions only. All right, now let's work on part B. Part B says, what's the pH when we add 51 milliliters of the NaOH? Again, to 50 milliliters, our reaction stays the same. What we start with stays the same. But there are some changes. So over here we had 49 milliliters, right? This has to become 51. Yeah. Part B of this question asks what the pH is when 51 milliliters of the base is added to the acid. That's where I'm at. Total volume changes, right? What's our total volume now? 101 milliliters. Our goal is still pH. In this case, our 5.1 times 10 to the negative third is our change. Now, how much of this 5.1 times 10 to the negative third is actually going to be reacted with the H plus? Only 5 times 10 to the negative third, right? So we're going to put that here. Our hydrogen is going to be completely consumed, correct? Okay, how much of this actually gets subtracted then? Just the 5 times 10 to the negative third, right? So what should be left here? 1 times 10 to the negative fourth. And now we're dealing with OH concentration. Now, remember, you're asked pH. In this case, we're going to get concentration of OH, right? What are we going to do? Take the POH, subtract from 14, and figure out what pH we're at. So one additional step in this type of reaction. The important part of titrations is that you follow this part. The rest of it, I know you can do stoichiometry. I know it might be rusty in your brain and you might not love it, but I know you can do stoichiometry. I know you can calculate a concentration. But this is the part I need you to understand. That all of this will react with as much of this as it can, and if there's leftover, that's what you're looking for. Yes, ma'am?
So nothing really matters on the product side of the reaction side?
Correct. In these types of reactions, with acid-base reactions, strong acid, strong base. That's what we're working with right now. Specific type of condition. How do you know if something's a strong acid and a strong base? You're supposed to know the strong acids from a chapter and a half ago. Okay? All right, what goes on the bottom? Because we're not in concentration, we're in moles, right?
Yeah.
So what goes on the bottom? Again, comes out to be about 1 times 10 to the negative third. In this case, I'm going to take a POH because I have OH concentration. My pH comes out to be about 11. I'm going to remind you, we saw a curve that looks something like this on Friday. We saw small values. We just did a calculation that told us what the pH was right before the equivalence point. And then we did a calculation right after the equivalence point. So we missed the equivalence point altogether. Could we get closer and closer to that equivalence volume? We could. Could we go and we do a calculation with 50.5 milliliters and 49.5 milliliters? Yup, that would get us a value that was closer and closer to this one. Just remember, at equivalence, the moles of the acid equal the moles of the base. That's the big takeaway about acids and bases. All right, let's look at the weak situation. So what do we know about weak acids and weak bases? Say again? They do not dissociate completely. They don't react all the way. So this one says, calculate the pH of the solution that is formed when 45 milliliters of 0.1 molar NaOH, which is a strong base, right? You agree? Yes. Okay. Is added to 50 milliliters of 0.1 molar CH3COOH, a weak acid known as acetic acid. And we're given a Ka for some reason. All right, so first thing we want to do is understand what the actual reaction that's happening is, okay? Remember, it's usually acid plus base makes something plus water. So let's write it out. The base we're adding here is NaOH. Does the Na matter? Remember, it doesn't. All right, so talk to me. What's going where in this reaction?
H was OH negative, so H2O plus.
So this guy is going to be my proton donor, right? Don't forget those definitions, Bronsted-Lowry's, but we're still using with this type of chemistry. So this guy's going to give its proton up to who? This guy, right? So this H is going to join over here. We're going to get H2O. Good, that's one of the things we know we should get. What's the other thing we're going to get? That guy, the conjugate base of the acetic acid. All right, from there, let's get everything into moles. We've talked about this before. Why are we going to get everything into moles? Because we really can't do math with different concentrations and different volumes unless we use molar amounts, okay? So let's get our moles of NaOH, right? That's a big one. What else can we get moles of? Given the information we're given? The acid, right? Okay, so we were told 45 milliliters which is 0.045 liters of the base, which is at 0.100 moles per liter, remember? I got 4.5 times 10 to the negative third moles of OH minus. The other one I've got 50 milliliters of the acid, again 0.100 molar, so moles of CH3COOH over 1 liter. From there we go ice table. In strong acids and bases, do we have to worry about anything on the right side? No, we did not. In weak acids and weak bases, we do. So we're going to do this just like any other ice table. Remember, there isn't anything for us to put in for water. We can put stuff in, right? So the first thing is, we know that this is what we started with. We know that theoretically, this, right? In this particular case, do we know what X is? We do. All right. Now, something we have to remember is that typically when we do acid-base chemistry, when we add basically what we need to remind ourselves of is the fact that when we do something with this acid, typically this acid dissociation is dependent on how it behaves when it's added to water, right? This is the new stuff. These two are not the same, are they? They are not. In this case, we used a strong base. In this case, we use a weaker base known as water. But when we do this reaction, look what we get. Our goal for this reaction is to figure out what the pH is, aka what is H+. Okay? Now, typically, if we go through, we get a Ka for this expression, right? It has H3O+, it has CH3COO-, and then it has the acid on the bottom, and we ignore water, right? You're with me so far here, hopefully. You remember this kind of, sort of. All right, we're going to assume that we can solve this using information from here to find H plus. So this is the new stuff, right? This stuff we've already talked about. We talked about this with our strong acids and bases. We know the base is going to completely react because it's strong, okay? But it is going to leave some leftover acid, and it's going to form some of the conjugate base. All good, because then that means we can use the Ka value and the Ka expression to solve for H plus. Now, if we made an ice table here, okay, and we knew this, we knew this was a nothing, we would usually plug in X here for H3O plus, right? And then we would have CH3COOH be the 4.5 times 10 to the negative third. In this particular case, we're not assuming that X and 4.5 times 10 to the negative third in the acid equation is the same value. So what we're going to plug in to our Ka expression is all the numbers we know. So we know Ka, right? We were given that. 1.8 times 10 to the negative third, fifth. We know CH3COO minus, it's 4.5 times 10 to the negative third. We know the acid concentration is 0.5 times 10 to the negative third, or 5 times 10 to the negative fourth. And then we're just going to plug in an X for our H3O plus. Can I erase this? I need to do something here. Before I do any of that, are these in moles or are they in molarities? These are in moles. How do I get them into molarities? Let's divide by the volumes. The total volume is 45 plus 50, so 95. So we're going to divide both numbers by 0.095. What do we get? I got that. 5.3 and then 4.7. 4.74 times 10 to the negative second molar here. Do your numbers agree? Negative 2. This one? Negative 2. It doesn't look like a 7. I meant 2. Fine, I'm sorry. I'm sorry if my markers are kind of being sucky. Switching again. All right, so I'm going to take this expression. I'm going to start plugging my numbers in. First thing I'm going to do is I'm going to rewrite it before I even try to solve for x. Now, good news is this is not a quadratic. These situations should not, for the most part, come out to be quadratic equations. They should be numbers at equilibrium. I know, I like to lie. Give you a false sense of hope and then crush you. It's my favorite thing. All right, so are we okay if I do this? Too bad. My concentration of this guy was 4.74 times 10 to the negative second. My concentration of this guy was 5.3 times 10 to the negative third. My x, which is my concentration of H plus. So the good news is we don't have to do any math at the end except for the pH. Yeah.
Where did this,
You're good? Double check your math and make sure it matches mine. Okay. So then pH. What'd you get for pH, Carly? Yeah, I got 5.7. Okay. Remember that this is a strong acid with a strong base. Remember that our pH curve is much shallower. So our pHs down here are closer to 3 to 5 prior to the equivalence point. And also remember that equivalence points of weak acids that are titrated with strong bases are greater than 7. One of our big takeaways from last week. All right. So the weak acid titration is much more intense. And with the strong acid-base titration, we could ask you at several different volumes, right? We could do the same thing with a weak acid titration. You could go in and you could do this with, instead of 45 milliliters, 52 milliliters, right? Hopefully beyond the equivalence point to see the other side of the titration curve. When we do that, we have leftover OH minus and none of the acid. If we have leftover OH minus, do we have to do this step? Heck no, we do not. Why? Because we can use the OH minus concentration to find POH and then find pH. So we're going to do that next. So we're still dealing with a weak acid being titrated with a strong base. I don't think this is one up there. I'm just going to do this one. Yes?
Right, so for 0.95, you divide that by the mole to get everything in
Right,
the
so
mole.
remember, we put moles in our table on purpose, right?
And then you convert.
But in order to do anything with KAs, you have to put in concentrations. Good question. What's up?
For grinding point, why did you use NA again?
Because Na is like a spectator ion.
Okay.
So over here, this would technically be Na plus with the CH3COO minus. It's a spectator, as we talked about way back when we introduced these in chapter 4.
Okay.
So it doesn't matter. You could leave Na in, but your big thing has to be that you recognize that OH is a base and this is the conjugate base if you do that. And that can be difficult for some. Okay? All right, so I am going to adjust the problem. The problem we are going to do is 52 milliliters of the 0.100 molar NaOH added to the original 50 milliliters of the weak acid. So, different. You'll be different. You'll be different. All different. Okay, so the one thing that doesn't change is this guy. Because we're still going to do 50 milliliters of the weak acid at the 0.100 molar strength. This time, though, we're going to add 52 milliliters of the 0.1 molar NaOH. Okay, so we want to put it into moles, right? Because that's what we've been doing. So we're going to do 0.052 liters. This one you're actually going to do with the calculator. I don't have these numbers worked out. I want to show you why you don't have to do the second half of the problem. You don't have to worry about K's in this problem. We'll see here in a second why. Yes?
Off the top you're doing is that an NaOH and then
What'd you get?
5.2 times
Okay? That's our number of moles, right? Of OH minus. Okay, so that's what's going to get added here. That's going to completely wipe this out. And that's going to leave behind 0.2 moles of OH here. Oops, 0.2 times 10 to the negative third, right? Is that going to form something over here? Probably. But only the limit as to what we actually consumed. All right, the question was, what is the pH at the equivalence point, or at the end of this titration, right? We have an OH minus concentration. Do I have to go through the Ka route?
No.
I don't. Because if I did, I'd be plugging a 0 in, right? I'd be doing Ka equals X times it's not going to work out for us. We don't want to do this, okay? Instead, we can get a calculation using this OH minus concentration. Do we know what volume is present?
Yes.
What? 102 milliliters. How'd we get that? We had 50 milliliters of this guy. We had 52 milliliters of this guy. So we're going to divide this number of moles by 0.102 liters. And what do we get? I do. What'd you get? Gotta do the math.
How did that overlap?
Oh, so 0.2 times 10 to the negative third just became 2 times 10 to the negative fourth. I just moved the decimal. I can leave it. Do you want me to leave it?
That's fine, you can do it, but I'm not gonna do it.
That's okay. You don't have to. You can do 0.2 times 10 to the negative third in your calculator. That's fine. Yeah?
Why wouldn't you subtract 5.2?
What do you mean?
Like, why wouldn't it be negative? Or-
So technically it would be, but since it would completely consume over here, there would be left over, is what we're saying. But the only amount that's actually going to react is the amount of acid present. We can't react any more than 5 times 10 to the negative third because that's how much of this we had.
It's not able that works.
Say again?
It runs out from 2 times 10 to the negative
All right, what do we do next? We're trying to find pH. We're going to take the negative log to get POH. What does that come out to be? Say again? So what's our pH going to be? Should our pH be that high? Think about it before you answer, and then tell me why. Raise your hand. Shelby, you're nodding. Tell me. So you added strong base, correct, and we started with a weak acid. Over the course of this titration, what happened in this second part? The weak acid got completely consumed, right? And there's leftover base. Leftover base should have a high pH. So in this type, or this part of a weak acid-based titration, we can skip that second half using Kas. So if you're before the equivalence point with weak acids and bases, you can skip you can't skip the Ka, right? After that equivalence point, though, if you have leftover OH minus, you don't have to do that part. Yes, sir. This one? I moved, it was 0.2. It was 0.2 in here. I wrote 2.0 times 10 to the negative fourth, and I think it confused. But then I just moved it back. So this is moles of OH divided by 0.102 liters. Should get you 2 times 10 to the negative third. All right, tomorrow in class, we're going to be working on these on our own. We have one more to go over, and it's on the equivalence points, and we'll talk about what that means tomorrow. Nope, just finish your outlines. Yes, ma'am. On the what?
So pursue my dreams. Yes. There's no point in delaying it. You gotta do it eventually.
Right?
So we run like
All it is time.
Well, so they all show up.
Okay, speed run life any percent. You can't just
yeah, I know.
stop any time.
Any percent. I will have the bishop around the record.
So right now you have record.
Hey, Miss Shep. What's up?